Tell me, what is your doubt? You're muted, Sojourner.
Okay. Okay. In the equation 1.9 and 1.10,
Just a minute.
page 7.
Yeah, 1.9. Yes.
Yes, ma'am.
So this is
Here, when
just
we,
about the orthogonality of the wave functions, right?
yes, ma'am, that's okay.
Hmm.
But I did not understand how they changes from the coefficient C to coefficient C bar by changing by changing the indices as quantum number to the occupation number, and there is a extra term comes where summation over E1 up to En uh, in the constant N1 into up to N infinity 1, and I did not understand how this term comes.
No, see, what is happening is that you can just do the summation over all quantum levels, right?
Yes, ma'am.
That's your first index, just 1, 2, 1, 3. I mean, you are not trying to see in the beginning which level is occupied by how many particles. Suppose you just collect what is the quantum number for each particle. Okay,
Yes, ma'am.
so that is one coefficient. But then you can also rewrite the same thing in a smarter way by saying that first level is occupied by say 5 particles, the second quantum level is occupied by 8 particles, and so on.
Yes,
Right? So that coefficient,
yes,
why do you think that coefficient should be exactly same as the earlier coefficient? It might not be same, right? Because now you also
yes,
have to include the degeneracy of every level basically. Right? So you're just splitting the sum so basically you're just rewriting the thing in a different way by saying that it is, since the particles are indistinguishable, so what is important is that what is the occupancy of each level. So here it is clearly written, right? All of those terms in the expansion of the wave function with n1 particles in the state 1, n2 particles in the state 2, and so on have the same coefficient in the wave function.
yes,
So basically, it is the property of the permutation of particles. So if you permute, say, first and third particle, but both of them have the same quantum number, nothing changes for bosons, right? The wave function will
yes,
remain the same.
yes,
You understand? Suppose the
yes,
first, you say that the first you write the first boson, or you write the later on you write the third boson, but both of them have the same quantum number. So as long as you have the same number of bosons in your first level and the second level, but then in the one configuration is that the first and third bosons are there in the first level, but the second configuration is in which say fourth and fifth boson, some other bosons are present in your first quantum level. So these two configurations are going to give you the same wave function because the particles are indistinguishable. So basically, you don't have a way to tag a particle and say whether first and third boson is present in the first level or fourth or fifth bosons are present in the first quantum level. We don't have that option, right? Because the particles are indistinguishable. So
yes,
that is why all the states which have a fixed number of particles in a given quantum level, they will have the same coefficient. That is the equation 1.7 first of all, right?
yes,
And then he's just trying to normalize the wave function, which is represented by the standard equation mod psi square integral is equal to 1,
yes,
right?
yes,
After integrating over whatever the relevant coordinates like real space or momentum space. It depends where you are writing the wave function, right? Now the resulting normalization will give you a condition like this,
yes,
where you are saying that sum over all quantum levels of mod square of this coefficient for being in a certain set of quantum level is equal to 1, right? But
Yes.
now I am rewriting it in a different way, that I am not saying that first particle is in quantum level 1, second particle is in quantum level 5, and so on. I'm just saying that how many particles are there in one quantum level. Okay. So that is why you have a sum over n1, n2. So these are the occupancies of various quantum levels. And then you just multiply it with, so this number is just 1, so it doesn't matter, right? The second coefficient is just 1
And
because
due
it's a
to this,
product of 1.
term, basically we got the weight factor. Uh, I mean, how many number of boys each
Yeah, so
particle? I
that
mean,
is basically just taking care of the permutation.
yes, ma'am.
Yeah. So
But I did not
basically what?
understand how this come when we changes from 1.9 to 1.10.
No. So suppose you take the example of four particles, right? Suppose you have four particles and you have say four levels, four quantum levels. So can you write down the possible? Can you think of the? I'm still not completely okay. Sorry. Can you write down the possible configurations for it? Then you will understand. So suppose I take one configuration in which I say all the four particles are present in the first level. Okay. Or I can take another configuration in which two particles are present in first level, another two particles are present in some third level. So there are many such configurations possible, right?
Yes,
Now, given a fixed number of bosons in a quantum level, suppose you go for the configurations where every time you have two bosons in the first level and two bosons in the third level. But there are four bosons. So you have many options of distributing these two bosons in the first level and two bosons in the fourth level, right?
yes, ma'am. I understand in this
Yeah,
now.
so this is just a permutation factor. How you distribute, so it is basically telling you now, suppose I tell you four particles, four bosons have to be distributed in two levels. So in how many
Actually,
levels you
ma'am,
will distribute them?
when we changes the indices from the quantum level to the occupation number, there is a number of term in the summation also decreases. So we have to take into account the which term is
Exactly.
actually
So it is
dependent.
just the same way, right? I could have written the configurations directly that in one configuration, first particle is in quantum one, second particle is in third level, and so on, right? So then I will get, if you have say four particles and say four levels and three particles, how many configurations you will get?
4C3.
And the same number of coefficients you will get.
Yes,
But if you think them in terms of the occupancies, then the number of configurations will be less. Although each configuration has a many ways of getting it. You understand?
yes, ma'am.
Because I'm just saying that three bosons are there in the first level, but then you can and the fourth boson is in the third level, say. But which boson is in first level and which boson is in third level, that I'm not telling you. So that is why these permutations are there.
And if the particles are distinguishable, then the number of term in both the cases will be same. So we do not get
Then
this
we
problem.
cannot talk about occupancies, right? Then it is meaningless to talk about occupancies because we are not giving the complete information. Here, basically, I'm giving you the complete information even when I'm telling you what is the occupancy. It's just that the normalization needs to be fixed, right? Suppose you have red bosons, green bosons, and some blue bosons. Then how can you say now I will only describe the configuration by saying whether I have three bosons in first level, five bosons in second level? That is meaningless, right? So this occupancy of every quantum level, it makes sense only when your particles are not tagged, when they are indistinguishable. Okay.
Okay.
Okay, so is there any other doubt, or you have not read it beyond that?
I am read up to the field operator. I mean, big. before the degeneracy of degenerate electron gate.
Oh, up to that you're right. Very good. So you went through all these properties of the wave function is a Slater determinant, and then how do you obtain the anti-commutator for fermions based on this antisymmetric property of wave functions and things like that, right?
Yes,
And then the equation 1.51, which I was trying to explain in last class, like how do annihilation and creation operators work.
ma'am. Here I have another question. So
Mm.
in the equation 1.53, so
Mm.
they for the case of fermion they introduce another factor minus one whole to the power ss, where say the ss is defined as n1 plus n2 up to n is minus one. So why up to n is minus one?
Actually, I'm not able to read this ns minus 1 even with my specs on. Are you talking about the equation 1.54?
Yes, ma'am.
So the subscript is something else. That's not S, right?
Ma'am, this
What
is
is the
s,
subscript on capital S?
small s.
Oh, okay. That's a very weird notation. Anyway. So, what is your doubt?
Why the summation up to n is minus one?
So, do you understand the process that is happening? They are trying to explain you the anti-commutation rules, okay?
Yes, ma'am. Actually,
Yeah.
there is a phase factor comes, and how they say that the phase factor will be minus one whole to the power capital S
Yeah,
subscript
so
small
that
s.
because these are fermions, these are not bosons, right? And they anti-commute. So suppose, okay, let's look at this state 1.52, right? Where you have say n1 particles in the first level, n2 particle in the second level, and so on, right? Because you have operated a dagger 1 n1 times on vacuum and a dagger 2 n2 times and so on, right? Now suppose in some sh level, s can be say 5, okay? Suppose I want to annihilate a5, a particle from the fifth quantum level I want to annihilate. So now when my annihilation operator will act on this state which was created in 1.52 equation, then what will happen? First it will hit a particle which is in level 1, right?
Yes, ma'am.
But my annihilation operator is in level 5. It cannot do anything to the particle in level 1. So it
Okay,
has to
okay,
cross that. So
okay,
basically
okay.
what it
I
means is
understand. I
you
understand.
anti-commute A1 and A5. So what do you
Yes,
get?
ma'am.
You get a minus 1 to the
Yes.
power n1.
Each cross there is a minus sign comes. So
Not minus sign, minus 1 to the power n1, depending upon how many particles are there in that level.
yes,
So it can be plus or minus. Right? If suppose there are two particles, then you go beyond both of them. So it becomes plus. So for first level, suppose when you take the A5 beyond the operator for the first, so you have A dagger 1 twice because there are two particles, right? Are you understanding it?
yes, ma'am. Yes,
Suppose N1 is 2. So then you do it twice, right?
yes,
Although for simple fermions it will not happen because if you're just thinking of say all up fermions or all down fermions, then all N1, N2 can be either 0 or 1, right? So
yes,
then if there is no particle n1 is 0, then you don't pick up any sign because minus 1 to the power n1 is just 1. But if you have a particle n1 is 1 and when you commute and basically anti-commute a5 and a dagger 1, you will get a minus 1 to the power n1 based on this equation 1.48, right?
yes,
So until and unless you hit a dagger 5, it will not do anything, right? So
yes,
you have to keep moving your A5 backwards till you reach A dagger 5 and then it will annihilate the particle in the fifth level. Is it clear?
yes, yes.
Sitaram, are you following the discussion? So do you have any doubt here? You have read this part? See, you must go through this part very thoroughly, because otherwise there will be gap when we will try to understand some of the properties of other models. Okay, you will have to calculate commutators to find out the symmetries and conserved quantities of the model, and that's where you will need all this algebra, or even to understand the low energy excitations. Okay, so I think after that there cannot be any doubt. It is very simple, right? And Saujanya, do you have any doubt after this equation?
No, ma'am.
Okay, so why don't you complete reading this chapter? Okay, so degenerate Fermi gas, and let me just tell you briefly about what are the interesting things to look in the non-interacting Fermi gas. Conventionally, they call it degenerate Fermi gas. I don't like that word, but basically, it's just a non-interacting Fermi gas. Okay. So suppose you have a model of non-interacting Fermi gas, what kind of property do you expect from it, and why do you think it is interesting? Is it any real application of that? Is there any real system where do you think non-interacting Fermi gas can be a good model to start with to understand some of its properties? So tell me, any one of you. Where do you think we can use non-interacting fermions? Is it of any use? I guess both of you know it at some level, right? Hmm? Why people are teaching you non-interacting fermions? Come on, speak something. Okay, I'm going to close this book, hearing, because I have to share something else with you. You think about the question I'm asking. Have you heard of something simple called metal? Hey, you guys have not heard of a metal? You have to unmute yourself if you want to speak. Both of you are muted.
Yes.
Are you not able to listen to me, or what is happening? I can't repeat every question. Okay. So I'm asking this non-interacting Fermi gas, what is the use of that model? Where do you think it can be applied as the simplest possible
Free
model to
electron model.
understand? In
Free
electron
electron
model.
model.
Huh? What kind of electron systems?
There are basically there is a no free electron theory. It is assumed that there is no interaction between the electron.
Yes. So where do you think this free electron theory can be a good description for what kind of systems? What will be the significance of a free electron theory? Let's think of it this way. Suppose you just have non-interacting electrons. What do you think?
For
What
the
will
conduction
we
of
can get?
metal.
So if you just have non-interacting electrons, then what will happen? What can you say? What do you think should the conductivity be doing here?
Because the motion of the free electron basically charge follows, and that's why conductivity arises.
Yeah. So if so, I mean, very intuitively you can think, right? Your electrons are able to move without any obstacle in from one edge of the sample to the other edge of the sample. So of course the current will flow, right? Smoothly. There will not be any obstacle to the transport, right? If it is just a non-interacting electron gas. So this should give basically a ideal conductor, a conductor whose resistivity is basically zero, right? Because what causes the resistivity to be non-zero? Only when these electrons will get scattered either in materials which is not apart, like they can get scattered. So electrons are there. There is no material which has only electrons, right? The real material cannot have only electrons. What else it has? If you take any real metal, for example, which is a good conductor, like copper, we have copper wires in our electrical systems, right? Why there is a copper wire and not a wooden wire? Because copper is a metal, it's a conductor. So, do you think copper has only electrons in it? Why we can model it with a simple electron system?
It also has some impurities.
Other than impurities, there are some basic things, right? What an atom has everything in it, right? Not only electrons.
Yes, other thing also have, but it is not a perfect conductor, so it have a impurities. Due to impurities, it have already some resistance.
Yes. So when it scatters with the impurities, there can be basically and basically that slows down the motion of electrons, and that's what
Yes,
is quantized in the form of resistance. Or it can happen that electrons scatter with themselves also in reality, because electrons are charged particles, so there has to be a Coulomb force between them, right? So they cannot be non-interacting. Now, why in metals we can have a non-interacting picture? Because we believe that the non-interacting, in a metal, when you have lots of electrons surrounding one electron, there is a very good something called screening, if you have heard of. Okay, so basically the range of electron-electron interaction gets screened out. So effectively, you will have only short range interaction between the electrons, and then it can happen that uh, the way electrons go from one side to another. I mean, their kinetic energy is so large that that interaction is much smaller. Their kinetic energy. Then to the first model, as a first crudest model, you can just think of these electrons as the free electrons and see whether you can explain all the simple properties you measure in lab about how the resistivity changes with temperature, or how the resistivity changes when you change the density of electrons in the system, or you apply pressure, or how does the specific heat of this material change, or the thermal conductivity change, whether it satisfies something called a Wiedemann-Franz law. So you must have heard about Wiedemann-Franz law, right?
yes.
What is Wiedemann-Franz law?
Sigma by KT equal to constant.
You're telling me so many symbols. Huh? What is sigma? What is KT now?
Thermal, sorry, the ratio of electrical conductivity and the thermal conductivity at constant temperature is a constant. It's a constant value.
Yeah, so basically the ratio just goes linearly with temperature, sigma by kappa, right?
Yes,
So why do you think it is holds true for metals? Just intuitively, I'm not asking you to write an equation or tell something. Just from your common sense, if you think that a metal can be modeled by non-interacting fermions, do you think we will get Wiedemann-Franz law? Just intuitively, we are thinking. Okay, we are not doing any calculation right now. If I Yes, both are transferred by the electrons. That will happen even when they are interacting, right? Suppose I don't use this non-interacting model of fermions, but some interacting model like the way I was writing in last class, where Hubbard model, right? Where you have this U, N up and down kind of term, or there can be some more complicated interaction terms in the system. And your answer is partially correct, but electrons are the only degree of freedom which are transferring both heat and charge. But is it the only thing? So what decides a transport quantity? Say conductivity, right?
Phonon also transport heat.
Yeah, so when you're just thinking of a non-interacting electron gas, of course, you are assuming that the phonon contribution is very low, and that can happen when you are not at very high temperatures. Okay, so Wiedemann-Franz law doesn't hold at very high temperatures; it holds at low enough temperatures. Low temperatures, low compared to the Fermi energy of the system. Okay. So what Sitaram pointed out is in some sense correct that both the transports are happening only through electrons. And so there are systems where you will see there is a separation of spin and charge. So it can happen that the charge is frozen, but the spin is still conducting. So you will see that once the charge is frozen, you cannot have a charge transport, right? So your charge conductivity will be zero because electron has both spin and charge, right?
Yes.
But the spins are conducting, spins are not frozen. So when the spins flip from one side to another, there can still be a transport of heat current in the system and also a spin current in the system, but there won't be any charge current propagating in the system from one edge of the sample to another. So in such systems where there is a spin charge separation, that is one example, and that happens when the system has strong electron-electron interaction. We will see when we will study Hubbard model in detail how come the spin charge separation comes in this simple model of electrons, interacting electrons, which may give a violation of Wiedemann-Franz law because the spins will be conducting, so there can be a heat transport, but there won't be any charge transport. Okay. But in simple systems where electric spin charge are basically behaving like as one identity, and it's basically the electron as a whole which is freely moving, then of course you will see it's the same kind of scattering rate or the scattering time of electron that appears in both the charge conductivity as well as in the thermal conductivity. Okay, so for all these simple systems where experimentally we see that the charge conductivity is good and thermal conductivity is also equally good and Wiedemann-Franz law holds, we can to some extent very confidently forget about the interactions in the system and just go ahead and use the simple non-interacting Fermi gas or the fermions on a lattice, just non-interacting fermions on a lattice to understand the basic physics of the system. Okay. So that's the simple motivation for studying non-interacting electrons. I mean, it should give you basically all the properties of a metal. I mean, metal has a good refractive index also, right? If you put an aluminium sheet in the sunlight, it shines light, it reflects back light. So even that reflection, high reflectivity will come because electrons are just free. So they can basically absorb energy, they will also emit energy. So all the properties of metal can be explained to some extent, I mean to a large extent, of simple metal. When I'm saying metal, I'm talking about simple conventional metals, not something like strange metal phase of the high TC superconductors, which has many question marks associated with it. But simple metals we can explain using the non-interacting electron gas. Okay. So now, what will be the simple lattice model for the non-interacting electron gas? Based on our discussion in the last class, can you tell me what will be the simplest lattice model you can write for a non-interacting, for a metal, assuming that electrons are just non-interacting? What will be the simple lattice model? Last time we were writing some models, right?
And non-interactive means we do not have any potential energy term.
Huh. So based on our last class, can you tell me what Hamiltonian should I write using the annihilation creation operator for fermions for a ideal metal or an ideal conductor?
As we only have the kinetic energy term, so
So how do you write it in a? I'm not asking to write it in continuum. You know how to write it. But
and kinetic energy, for the case of kinetic energy, we have to write in terms of creation annihilation operator by either using number operator like a dagger a or c dagger c.
so what term
And
should I write? What term should I write? How the kinetic energy will look? Just tell me the term.
okay, Hamiltonian laws. First, we have to take a constant hopping term. So
Hmm.
let us take a minus t.
Hmm.
So and summation over. we have to take two indices I and j, summation over ij. So a dagger, a dagger I,
Hmm.
and if there is a spin included, then we have to include a spin within the creation and annihilation operator. So it will be a dagger,
Hmm.
I sigma, a I sigma, a j sigma,
Okay.
and plus its Hermitian conjugate.
Mm-hmm. So why there is a minus t? You said something about minus t. Can you tell me why there is a minus t?
Minus is basically due to the convention.
Why that convention? There must be a logic behind the convention. What goes wrong if I take plus t? What goes wrong if I have plus t? So are you able to see the Jamboard from the last class? So this is what you are telling Saujanya, right? This is the kinetic energy term written in a discrete sense on a lattice minus T C dagger I sigma C2 sigma. Okay, so what is sigma is the
Spin indices.
spin of the electron. It can be up or down, and Ij are the what are Ij? Well, Ij are simply site indices, right? Isn't it? I don't hear you. I think you are muted.
Are you writing something?
Where? I'm not writing. I was just showing you this board. Are you able to see the board from the last class?
Yes, sir.
Huh. So here it is written, right? C dagger I sigma, Cj sigma.
Yes,
You're able to see, right?
yes.
Yeah. So Ij are the site index, right? So how do you choose this Ij? From where, if suppose I is 1, what j can be?
It's neighboring hopping. I plus one or I minus one.
Why it has to be always neighboring? Is there a rule?
If a electron try to hop to another atom, first it hop it to its neighboring atom, then it can hop to another neighboring atom.
Yeah, but
So
what stops it from directly hopping from, say, first site to the 50th site?
due to the periodic arrangement of lattice in crystal.
No, that's not the reason actually. So the actual reason is what this hopping process represent. This actually represent that you have overlap of orbitals, right? You have to think little bit in terms of chemistry now. So you have this electron orbitals sitting on various sites. Sites are basically the potential wells created by the ions on which the electrons are sitting, and then they can hop around, right?
Yes,
So every electron has its orbital. So it is very natural to think that the electrons which are adjacent to each other on the adjacent ions, their electron orbitals will have maximum overlap, right? And because
yes,
of that overlap, basically you can think as the electron from, say, the first orbital or the first ion has moved to the second ion or second site, and vice versa. Right. So why do we have Hermitian conjugate? Because we are thinking of a system where the particle number is conserved. Particles are not getting lost from the system. It's an isolated equilibrium system. These particles are not getting lost from the mod system. We're just thinking of particles moving inside the system. That's why there is a Hermitian conjugate, that if a particle moves from I to J, some other particle must have moved from J to I. So that the process is Hermitian. Otherwise, the symmetry in the system will break. Okay, so since the overlap between the electron orbitals on the adjacent site is maximum, you will assume, I mean, it will happen if you really calculate starting like a chemist, what is the amplitude of the hopping, it will come out to be largest for nearest neighbor sites. And then as you go to farther sites, since the overlap between the orbitals of the electrons is smaller, the coefficient of further order hopping is actually smaller. So there is actually in a metal, there will be many range of hoppings. You know, particle can hop from first side to second side, neighboring side, it can go to second neighbor or third neighbor, but those amplitudes are generally smaller, much smaller than the amplitude of hopping from between neighboring sites. That is why we just start with the work with the simplest model most of the time, which has only nearest neighbor hopping. Okay, but many times from the experiments, from where we can measure the density or state of the system, we know that nearest neighbor hopping is actually doing very bad. We should have at least the second neighbor hopping added to the model, then we get the kinetic energy correctly. But the reason that we mostly keep only nearest neighbor hopping is because the amplitude of nearest neighbor hopping is largest and other terms are comparatively smaller. Okay? Now the second question comes. Is it clear what I said just now?
Yes, ma'am.
Okay, good. So now the second question comes. Why do we have a minus in front of the hopping term? Think about it. Why do we have a minus sign? What changes if you don't see? The simplest way to answer a question is you think of the situation when you don't have a minus sign and then see what changes if I don't have a minus sign. Suppose you have a suppose you have a plus t, what will happen? Okay, this is something you should think, huh? And give me the answer in the next class. Now tell me, suppose we start with this model that is there in our Jamboard. Where did it go? Right. So you don't have a U term, you just have the kinetic energy term in the Jamboard, in the model. So how will you solve this model? If I ask you what is the ground state of this model, what will you do to find out the ground state of this model? You just have the term minus T C dagger I C J sigma plus Hermitian conjugate. What do you think should be the ground state of this model and how will you find out that ground state? That's what most of the time in condensed matter physics we do, right? The first thing you do is find out the low energy properties of the system. So you find out the ground state and low energy excitations of the system. You have all done non-interacting Fermi gas, right? In some form or the other from Patharia and other books, I guess. Now I'm just writing it in a slightly different way, in a discrete, on a lattice. These are the free electrons hopping around on a lattice. So what ground state you will get? And how will you go ahead to find out that ground state? Any guess? It's very simple. We already talked about it partially in the last class, right? What is the ground state of a non-interacting Fermi system? Come on, speak up. Unmute yourself and tell me what is the ground state of a non-interacting Fermi system? You don't know or you don't want to tell me? If you don't know, you say you don't know, at least, so that I can tell you. Both of you are muted. I don't hear anything. Tell me what is the ground state of this non-interacting fermions?
I don't know.
You don't know, okay. You never heard of a Fermi gas?
Yes.
So what is the ground state of a Fermi gas? How do you fill up electrons in a Fermi? So what will happen? Okay, let's look at the model and let me explain to you in a very simple fashion. So you have this model, right? Minus T C dagger I C J sigma. Uh, Forget about the word Fermi gas. This is a quantum Hamiltonian, simple quantum Hamiltonian. How will you solve it? So right now, so what does it mean to solve a Hamiltonian? Hamiltonian can be written in form of a matrix, right? If I
Yes.
choose a basis for my problem, I can write it in terms of a matrix. So for example, this one is a matrix. So if I choose the basis of this single particle system, and how will I write my Hamiltonian matrix? So suppose I want to write a term minus T C dagger 1 C2. It means the particle has hopped from 2 to 1.
Which page you are writing?
I am not writing, I am just showing you the Jamboard. Is it not visible to you? The Jamboard is not visible to you.
Yes, and Jamboard is visible, but previous lecture note is visible.
I'm not writing right now, actually. I'm just verbally telling you. Because somehow my pen got the nib of that pen is not working properly. So I'm not able to write it right today. That's why I'm speaking or sharing things from the earlier thing. Okay. So please manage with it this time. Hopefully by next class I will have my new pen with which I can write on the screen. So right now I'm just showing you this minus T C dagger I C J sigma, right? So how will you
Yes.
solve? Go ahead and solve this Hamiltonian matrix. First tell me what will be the matrix representation of this Hamiltonian. Okay, I can try to write something for you people just using the mouse directly. So suppose I choose a basis. I want to write it as a matrix. Right? Now, what is the basis? The basis I will choose is say C dagger 1. Let's forget about the spin for the time being, okay? C dagger 2 and so on. Let's consider only two sides, okay? C1 and C2. So how will I write this hopping term in this matrix in form? There is no hopping from 1 to 1. There is no term like C dagger 1 C1. So I have a 0 here, right? Then you have a term minus C dagger 1 C2 minus T. So here I have a minus T. Right. Similarly, there is a term C dagger 2 C1, which is just Hermitian conjugate of it. And if I assume that T is real, I get a T here. and then I have another 0 here, right? So if I just have two sides, this is how you will get a matrix for your Hamiltonian. Are you able to see what I'm writing now?
Yes, ma'am.
Yeah. So now the question to some extent is how do you solve this matrix and get the eigenvalues of the system? So the simplest way to solve any quadratic Hamiltonian is you do the Fourier transform. So I
I mean,
basically
if it
write,
was a block diagonal, then we can find the
so if
eigenvalue of each block.
So if it is already much simpler than that, I have written only a 2 by 2 matrix. So you don't need to block diagonal means it will become diagonal automatically,
Yes, ma'am.
right? So when we say we solve a Hamiltonian, then it basically means you know some of the eigenvalues at least and the eigenstates. Okay. So if it is a simple quadratic Hamiltonian, the simplest way to solve the Hamiltonian is, I think this is also described in Fetter and Bollica, how to do Fourier transform. We were talking about it last time, right? So I just do a Fourier transform of this operator. Okay. So if you do a Fourier transform, oh, it's so difficult to write without my pen. So k dot ri basically, you just do a standard Fourier transform. Now, what will happen to this Hamiltonian? Tell me. The Hamiltonian that I was showing you minus Tc dagger Icj, that should just become, let's suppose we take only a 1D chain, okay? And then you do a Fourier transform. What do you expect to get? Your Hamiltonian will simply become minus 2t. Okay, let's just give me a minute. Okay, it's becoming. Let me write with what is then I okay. Are you having other classes online or how is it working? So okay, let me write. So let's see if it works. It's not that bad. So this is the Hamiltonian, right? We have. Can you see it now? Yeah, are you able to see what I'm writing? So now you do the Fourier transform. So Ri is the spatial index of that point, and then you just do a simple Fourier transform and get this Hamiltonian. Okay, now tell me what will be the Hamiltonian after the Fourier transform. Sorry, this is Ij sigma, I'm just writing it like that. So how should I do the Fourier transform? I basically need to use the reverse Fourier transform here. So I will get some C dagger K sigma, then I will get some other Ck prime sigma, and then we will have I K minus K prime dot Ri and minus I K prime dot delta. So I have used something. Do you understand what I have done here? So I'm writing this now not only for one-dimensional chain, but say for any generic lattice where there can be a hopping from say site I to j. I'm not even confining it to, so right now I'm confining it to say nearest neighbor with delta the nearest neighbor vector. So if you are on two dimension, your delta can be delta x or it can be delta y. And then correspondingly you can have a minus delta x and a minus delta y. Okay. So do you understand the step in equation 1 that I have written, starting from equation 0? Tell me yes or no so that I can go ahead. If you just sit like this, how can I teach? Sajanya, is it clear to you what I have done?
Yes, ma'am.
So then you should tell, right? There are not 50 students in a class, only 2 of you are there. I have asked 5 times. Is it clear? Then I can write, go ahead. So you should tell me. So now tell me what will be the final Hamiltonian based on this? What should I write for the final Hamiltonian based on this? Once I have done the Fourier transform, what do I get? Of course, plus there is a Hermitian conjugate term which I forgot to write here. So what do you get now at the end? What do I do with these exponential factors? Do you know how to do it? Tell me yes or
No,
no. Okay,
no.
let's use some of the properties of the Fourier transform and some of simple properties of the exponentials and delta function. So I rewrite it as sum over I and delta and sigma. Then I have and of course a sum over k and k prime. Now look at this sum over this term, okay? Let me remove I from here. Let us write I here and say what is this? What do you think this sum will be? If I have a sum over I exponential minus ik minus k prime dot ri, what I should get? And then this,
A direct delta function, delta of k
yes.
minus k prime.
So you get a direct delta function. That's very good. So what does it mean? So we are basically left with, I have a k prime. Now the sum over I has gone because we got a direct delta function, right? So I write here k sigma, k prime sigma plus Hermitian conjugate I'm writing. And then you have a e minus I k prime delta, and then you have a delta k prime, right? Is it clear now? So if I just use the delta k prime over this sum over k and k prime, then what happens? What will happen? What does sum over k and k prime multiplied with a delta k prime and some other function of k and k prime gives me? This you should be able to tell, and you have to tell. Hmm? What do I get by sum over k prime delta k prime? Sitaram. So basically, when you have a delta function,
Number of
other index will disappear, right? If you people already know these things, then I don't need to spend time. You have to tell me because then you get more time to learn new things. But if you don't tell me and sit like this, now tell me what do I do? So what is the final form? Can you tell me now? After taking care of this E minus I k dot delta. Suppose we are in 1D. What are the options of delta now in 1D? Plus x or
Plus
minus x?
minus one.
Hmm?
Plus one.
So
Plus
in
minus
one,
x.
right. So in 1D we just get the operator part I can write because that's common. Even if I do the Hermitian conjugate, I will get the same operator. So I just have E minus k dot delta plus E I k dot delta, right? Sum over delta. And what does this give me? This just gives you 2 times cos of k dot delta, right? And the way to do is, see, although you have both plus x and minus x neighbors, let's just, so
If
you
I
have
take
some,
the
tell me.
nearest hopping, so the x equal to the lattice constant then.
Yes. No, what I'm trying to tell you is for every hopping, you have a plus x and a minus x bond, right? So you can hop from here to here, that is plus x. If you hop from here to here, then your delta is minus x, right?
Yes, sir.
So now, but you don't have to do sum over both plus x and minus x because then you will be over counting. So you have to understand this thing. So see, these are your sides 1, 2, 3, 4, and so on, right? So there was a sum over sides. I have already done sum over all sides, right? That's how I could replace the exponential minus k prime with the delta k prime. So since I have taken sum over all sides, I should look at only one type of hopping. So for example, I can see that 1 goes to 2 and then 2 goes to 3 because the Hermitian conjugate will automatically give me 2 comes to 1. So there is no need to consider 1 goes to 2, then Hermitian conjugate of it, and as well as considering the hopping 2 to 1, which corresponds to minus x value of delta. Because then you will be counting this bond twice, right? Do you understand this part?
Yes, sir.
So that is why, so effectively you will have only minus 2t sum over k sigma cos k c dagger k sigma c k sigma. So this is the simple Hamiltonian for the non-interacting fermions moving around in a one-dimensional chain with periodic boundary conditions. Where did I use periodic boundary condition?
Delta equal to plus minus x.
No, that's not the periodic boundary condition. The periodic boundary condition is already defined, used at the moment when
Okay,
I,
we have used the plane wave basis e to the power I
right.
clear.
So when I'm doing the Fourier transform, I have already used the periodic boundary condition and in the allowed values of k. Okay. So now the next question comes is, what are these k's?
As we use the periodic boundary condition, so k must be the integral multiple of pi by lattice constant or pi by x.
So how do we find out what are the allowed values of k now? Now we have only kx basically. So what are the allowed values of kx? How do I choose that? Do I have a freedom or it is given by some property of the system?
We have to see that for which value of k the Hamiltonian is non-vanishing.
And that's not the way. You have to use the property of the wave functions. You did the Fourier transform, right? And in that Fourier transform, if you want to say that the n plus 1th side is the first side, basically, that gives you the condition, right? So that gives you some E, I, K, R, N should be equal to 1. Some condition you will have like that. And if it is a 1D chain, this Rn is just basically the nth side, right? Times some lattice spacing A. So you basically have just some Na is equal to 1. What is this condition now? What does this tell you about K? Yes, so k should be some integer times 2 pi by na. So that fixes your brilliant zone for this chain. Okay, so you can have a brilliant zone going from minus pi by a to 2 pi by a, because m can take as many values as you have the sides. The degrees of freedom in the real space and the number of degrees of freedom in the momentum space must be equal. We cannot miss out any degree of freedom. So the values m can take goes from 1 to n minus 1 to n basically, or 0 to n minus 1, you can say, right? So that tells you your brilliant zone, which is from minus pi by a to pi by a. So once we know that, what are the allowed eigenvalues of this system? The allowed eigenvalues will be basically just a cosine on that range, right? So at minus pi by a, what is the value of cosine?
Plus minus 1
Plus minus,
cos.
plus minus 1 both, huh?
No, for plus pi by,
Cosine is
sorry,
a
plus 1
function. Cosine is
cos
only
pi
minus 1, right? Whether
minus
it is
1.
minus pi by a or plus pi by, it's an even function, right? So you will have basically, this is your kinetic energy of the system as a function of k, and at pi by 2 it will be 0, and here it is maximum. Sorry, at these are the pi by 2 points where it is 0, and this is 0 where it is minimum. It is equal to minus 2t here, and it is equal to 2t here, right? So you must have heard people talking about the bandwidth of a system. So what is the bandwidth? Bandwidth is basically the difference between the minimum and the maximum value. So 4t is the bandwidth of your system now. Okay. So now in this k, you have many allowed k levels, right? These allowed k levels are coming from here, from this k is equal to m 2 pi by na, right? So for every k value, you have a energy. So now what will be the ground state? So for every k value, you have certain energy, and the k values are bounded between minus pi by a to pi by a, or 0 to 2 pi by a, depending upon what convention you choose. So what is the ground state now? Suppose you have n electrons, so you have n sites, right? We started, that's why I have put capital N here. We have n sites. So how many maximum electrons you can have in this system? If you have n
2n.
sides, 2n electrons, you can maximum put. Okay, let's say the number of electron is less, is as many as the number of sides. Suppose we have some number. It can be anything. I'm just, for example, taking it to be as equal to the number of sides. So then how many k levels will be occupied? How will you distribute? So to find out the ground state, you have to find out how will you distribute the electrons in these quantum levels, right?
Yes.
Now it's just a question of, you know, what are the allowed quantum levels. They are given by minus 2t cos k, and then you know what are the allowed values of k. So the ground state will be when you distribute them distribute electrons in the lowest possible energy states till you distribute all the electrons. Right? So you start filling up the electrons in the lowest possible energy, and to keep filling them till you. So suppose you start putting electrons in the lowest possible energy, and every level, how many electrons you can put? 2 electrons, because these are spin half. So you keep doing that until and unless you reach Ne. So since the total number of what will be the total number of k levels, energy levels? The total number of energy levels will be 2n, because you have spin, and then you have n values of momentum. So you will have 2n values, right? And out of that, if I have, say, n equal to n, how many levels I will fill up? I'll put 2 electrons in every side, every level. And how many electrons I will fill up? So basically, you will have n levels, each having a degeneracy of 2. So I will put 2 electrons in every level. So how many levels I will fill out of n? I
n
will
by
fill up
2.
n by 2
2.
levels. Okay, so your metal, a good metal at half filling, will have half of the system occupied and half of it is empty, right? So your ground state will be, what will be the ground state now? The ground state will be that you have put all the particles till some maximum occupied level into your vacuum. And what is, right?
Fermi level.
Yeah. So this is n electrons you are putting, and this Kn is defined as the Fermi momentum, and the corresponding energy minus 2T cos kF will give you the Fermi energy. So the ground state is simply a asymmetric. So I have not asymmetrized this wave function. You have to asymmetrize it. So the Slater determinant that you obtain by occupying the lowest n by 2 levels, energy levels of your system, will give you the ground state. That is also known as the Fermi C. Okay, and then you have this Fermi energy here, which is the maximum energy occupied by this system. The corresponding momentum is the Fermi momentum. Here you have the Fermi momentum, and so what are the? This is the ground state, okay. But this ground state does not tell you whether this system can conduct or not, whether it is a good model for a metal or not. So how will you see that? You will have to look at the low energy excitations of this system. So what are the low energy excitations of this system? Think about it. We will do it in the next class. Okay, I have a meeting of the computer committee at 12 and I need time to go and join that meeting. So you please think about two questions. Simple question. Why the sign of hopping amplitude is minus? If it has to be minus at all. You told me it is minus t. So why is it minus? And second, you think, now we know that for the non-interacting fermions, the ground state is the simple Fermi C, where you basically populate electrons in the lowest possible energy levels till you have populated all the electrons. So what are the low energy excitations of the system, and whether these low energy excitations can help you in understanding the properties of a metal that you are familiar with. Okay, think about these two things. Now this is for the class. So now just to wind up, both of you have said that you will do this reading course. So I will announce it to Harvinder Singh, CCing it to you. And for the project, both of you want to do MBL, right?
Yes, sir.
So I will give you two different things on MBL, and for that I think it will be better if we talk individually so that I know your individual interest and then I assign the problem accordingly. Like I think Sitaram is quite comfortable with numerics. He knows Fortran and C both, right? So I can give something to Sitaram where he directly start with some numerical aspects. I mean, at least you can try to see how you like it, learn it, and see. At some point everybody has to do numerics for this complicated problem. So you start from there. But I will give a review to both of you to read. The reading part for the project can be common to both of you because the topic is similar. But then the finer things that you will learn to calculate and analyze, that will be different for both of you. Okay. So for that, I
Okay.
will send an email maybe next week sometime. In the meantime, I can send you, if you are really keen to start with the project, I can give you some basic review on many body localization just to give you people a feeling of what this field is about. Okay, so just read it like a storybook. I mean, don't worry if you do. There will be too many new terms, and it might be confusing for you. But to start with, you can just read it like a newsletter or a storybook. Just try to collect some information in keywords, and then we will discuss them slowly for your better understanding. Okay.
Okay.
And your homework for the next class is, of course, you will do these two questions that I have asked you. You will work on these two questions. And next time, I want to start. So we have talked a little bit about the metal, right? We will, of course, little bit more about it. But then the next topic, I want you people to read it. I will share it with you. So just give me a second. So there is a book by Fetter and not Fetter and Morica. There is a book by Fazekas. Okay, I gave a reference of it in my first class. It is called Lecture Notes on Electrons and Magnetism. So there is a chapter 4 in it, which I am sharing with you right now. Are you able to see it?
Yes, ma'am.
Yeah. So this is a chapter on Mott transition and Hubbard model. So this is the main beauty of the Hubbard model, that it can give you metallic phase as well as an insulating phase. But that insulator is very different from the insulator you are familiar with so far, like the band insulator. It is called the Mott insulator. So try to go through this chapter as much as possible once you are done with the second quantization. Okay.
Can you open the first page of this book? I mean the cover page.
Cover page. Okay. Uh, This is the first page. Lecture notes on electron correlation and magnetism by Patrick Fazekas. It's a very old book. I can give you the soft copy of the book. I'm not sure whether it's there in library or not. Okay. So try to read little bit about the fourth chapter. That will give you some background of it. And then in the next class, after finishing up some things on the non-interacting, once you tell me the answer to the two questions I have asked, we will move on to this. Okay. Okay, is it fine? So I will stop the class now because I have another meeting.
Okay.
Okay, so you work on your homework and I will send you something to read on MBL. Okay? Okay, then bye for now.
Okay.
Yeah.